something like this. So Faraday considered a, a small closed surface enclosing some positive charge Q. So it's like you take a balloon and then rub the balloon with fur. So you excite some charges on the closed surface. Okay, and then he takes a hollow sphere, a big hollow sphere, and this charge Q is enclosed in that big hollow sphere. Initially, the hollow sphere is earthed so that there are no charges present on the outer surface of the hollow sphere. Now he puts this small sphere of containing some positive charge Q inside the hollow sphere. So it's like you have a balloon, you rub the balloon surface with fur so that the charges are excited onto the balloon surface. Now you drop slowly this balloon into a hollow closed surface, or into a hollow spherical surface. So understand that there are certain devices that that help you in calculating or in knowing the amount of charge present in this surface. So there is a charge meter which gives the reading of whose reading is equal to the amount of charge enclosed by the surface. So initially, when this small surface containing positive charge Q is not placed in this hollow sphere, so the reading in the charge meter shows 0. That means there is no charge present in the hollow sphere. Now when he places a small sphere of positive charge Q inside this hollow sphere, he noticed that this reading changed to some value. And then when he removes it, I mean, if you consider it as a balloon dropping into a hollow sphere, if you pinch this balloon with a needle and then if you remove the balloon, still he finds that the reading, the meter reading in this charge meter doesn't change, which means that when the charge cannot reside on the closed surface, that means when you remove the closed surface, so the charge now gets displaced, and the charge that is displaced resides on the hollow sphere. So he tried to find out what is the charge present on this hollow sphere, on the outer surface of the hollow sphere, and to his surprise he noted that there was a charge of plus Q that is present on the outer surface of this hollow sphere, and hence he concluded that the total displacement is equal to the amount of charge enclosed by the surface. Is it clear to you? I'll repeat the experiment again. You take a hollow sphere, earth the hollow sphere initially so that there are no charges present on the hollow sphere, the large hollow sphere. Then you take a small sphere full of positive charge. It's like you take a balloon, you excite some charges on the balloon, and then slowly you drop the balloon into this hollow sphere which didn't have any charges, and then notice what is the reading in the charge meter. So that shows certain amount of charge that is present inside the sphere. Now pinch this balloon with a needle and then remove this balloon out. So when you pinch it with a needle, so it is no longer a closed surface. So if it is not a closed surface, now the charges cannot reside on this surface, so the charges gets displaced. That's what you noticed. The charges are displaced and then they reside now on the outer on the outer spherical surface. And how much is the displacement? So you notice the total displacement to be equal to the amount of charge enclosed by the surface. Now this is the total displacement that is observed, and understand that the total displacement always occurs on the outer surface of the hollow sphere, the big hollow sphere that is considered, right? Now you see how he's going to extend this concept to a big theory in itself. The next step, he considers that this hollow sphere, the outer hollow sphere, has a infinite radius. Okay, so the next step is you have this charge anyway, a small sphere of containing positive charge q, and now the outer sphere has an infinite radius. So if it is infinite radius, that means it is very far away from this charge q. So uh, practically the effect of this charge should be very minimum at a point which is very far away from this charge q. And if you take any point p which is at a distance of r from this charge q, if you take a point p which is a distance of r from this charge q, can you talk about the total displacement here? No, you can't talk about the total displacement here, because the total displacement can occur only on the outer surface of the hollow sphere, and that is at infinity. Since you can't talk about the total displacement at this point p, you can define the quantity called displacement density. Displacement density. What is line charge density? Charge per unit length. What is surface charge density? Charge per unit area. What is volume charge density? Charge per unit volume. Similarly, displacement density is total displacement by the total surface area. Right? And what is the total displacement? The total displacement is q. And what is the area now? Now this is not a circle. Do remember, it is, because we are talking about the points in space. So it is a spherical surface of radius r. What is the total surface area of sphere of radius r? That is 4 pi r square. And the displacement density, since we are talking about only the magnitude, so I will not show the vector form, but I will show it as only the magnitude. D, which is equal to q by 4 pi r square. Multiply by epsilon and divide by epsilon, so this will be equal to epsilon into 1 by 4 pi epsilon q by r square. And we already know what is 1 by 4 pi epsilon q by r square, right? This is E. So this is the relation between D and E. D is equal to epsilon E in their magnitude form. So without loss of generality, we can relate D and E as D bar is equal to epsilon into E bar. This is one of the simple ways of deriving the relation between D and E, as D is equal to epsilon E. There are several ways of relating D and E, or giving the relation between D and E as D is equal to epsilon E, using the cylindrical coordinate system or spherical coordinate system. There are some complex ways of relating these two these two quantities and prove that D is equal to epsilon E. However, I want you to understand a few important points here. One is the concept of the total displacement, that is equal to the amount of charge enclosed by the surface, and then the displacement density denoted by D, and D is equal to epsilon E, or D bar is equal to epsilon into E bar. This equation D is equal to epsilon E is valid only for isotropic materials. So we are going to consider two kinds of materials in our discussion. One is isotropic materials, the other is anisotropic materials. What is the difference between isotropic and anisotropic materials? Isotropic material is that material in which the properties of the material or the properties of the medium do not change from direction to direction. So they remain constant in all directions. And anisotropic material is that material in which the properties of the material or the properties of this medium changes from direction to direction. So it is not constant in all directions. If it is not constant in all directions, then you can't relate D and E as D is equal to epsilon E. That is the difference between writing down the equation for D for D and E for isotropic materials and anisotropic materials. So the equation D is equal to epsilon E is valid only for isotropic materials. I could uh, define isotropic material in terms of epsilon here. As I told you, the properties of the material remain constant in all directions, right? For isotropic materials, that means epsilon is constant for isotropic materials in all directions. So since epsilon is constant, so you could write D is equal to epsilon E or E is equal to D by epsilon. You can play with epsilon only when epsilon is constant, and that is possible only for isotropic materials. In isotropic materials, epsilon is constant. It is a number 3 into epsilon naught or 4 into epsilon naught. While for anisotropic materials, since the properties of the material is not constant in all directions, even though we write D is equal to epsilon E, do remember that epsilon is not constant in this case. Epsilon is not constant for anisotropic materials. That means it is not same in all directions. For your information, for the case of non-isotropic materials or anisotropic materials, the relation between D bar and E bar would be of this type: D1, D2, D3 equal to epsilon 11, epsilon 12, epsilon 13, epsilon 21, epsilon 22, epsilon 23, epsilon 31, epsilon 32, epsilon 33 into E1, E2, E3, which clearly shows that epsilon is not constant in all directions. So 1, 2, 3 can be considered as x, y and z directions. So it is like xx, xy plane, xz plane, similarly yx, yy, yz plane, zx, zy, zz plane. Right? So in the examination sometimes he gives you a matrix of epsilon, and then he gives you the components of E bar and E1, E2, E3, and then he may ask you to find out D bar, which is D1x cap plus D2y cap plus D3z cap. And if he says it is an anisotropic material, please use this relation and don't play with epsilon. You cannot write E is equal to D by epsilon for anisotropic material. Very important 1 mark question, frequently asked question in IES and other PSU exams. So which of the following equations correspond to or is a valid equation for anisotropic material? So when he says anisotropic material, then don't play with epsilon, just write D is equal to epsilon E. If he says for isotropic material, then you can write E is equal to D by epsilon because epsilon is constant. And if it doesn't mention anything about the material, then take it as a isotropic materials. Okay. In general, when during our discussion, we always consider isotropic materials only. In electromagnetic waves chapter, we will talk about isotropic media. So there it's the same. So here I say it as a material, there I discuss the same material in terms of media. There is one more media called homogeneous medium. Right? So it is a medium in which the properties of the medium do not change from point to point. At each and every point, the properties of the medium will remain constant. Okay. Anyway, isotropic and non-isotropic media are the media that are usually considered. So we will also consider the media as isotropic medium if the kind of medium is not explicitly given in the problem or if it is not explicitly defined.